Hello, my name is Shlomo Berger, and my research field is on nonlinear dielectric materials. These materials are crystalline and have a polar axis oriented towards a specific direction in the unit cell. The crystals have domains, which are regions of electric dipoles oriented towards the same direction. The domains are formed spontaneously and create internal electric fields inside the crystals. Applying an external electric field results in growth of the domains towards the direction of the applied electric field and a nonlinear change of the dielectric polarization. Our research interests are in developing highly sensitive detectors and sensors of heat, light, especially in the infrared range, and mechanical forces. High detection efficiency and sensitivity can be obtained in ultra-small crystals having high pyroelectric and piezoelectric coefficients and low dielectric permittivity. So the main challenges of our research are in developing or reducing the crystal size into the nanometer scale, but the more challenging tasks are to grow the crystals with uniform crystallographic orientation. In addition, we would like to fabricate a device that consists of an array of nanocrystals separated from each other, where the nanocrystals have a uniform size crystallographic orientation. This array consists of 100 billion crystals, where each crystal can serve as a sensitive detector of heat and light. So how do we obtain these challenges? So the design concept of our samples is as follows. Formation of a thin film template that consists of a highly dense array of pores made of amorphous alumina by the electrochemical anodization process. Then nanocrystals are grown inside the pores, having uniform crystallographic and polar orientation along the longitudinal axis of the pores. After the anodization process is done, a highly dense array of alumina pores is obtained. In this case, you can see a high-resolution SEM micrograph of the 100 billion pores per square centimeter. The average diameter of the pore is about 55 nanometers and a narrow diameter distribution of the pores. Vertical cross-section of the pores show the vertical orientation relative to the surface of the porous film. The pores are separated from each other by an alumina wall having a thickness of about 20 nanometers, and we grow the crystals inside these pores. So after the pores are formed, the next stage is filling the pores with the nanocrystals. The process is as follows. First, a liquid solution is inserted into the pores, where the liquid solution inside it, the dielectric material is dissolved. The next stage is nucleation of the crystals at the bottom of the pores. This stage is done by reducing the temperature of the liquid solution and causing precipitation of the dielectric materials. And the third stage is growth of the crystals inside the pores with a tight control of crystallographic orientation. At the end of the preparation process, the samples are taken out of the liquid solution and the surface is cleaned from any residual material. As you can see here, the pores are filled with the crystals and the surface is clean. Various materials have been grown in the pores in our laboratory, and I would like to give only one example to illustrate the effect of it. I would like to focus today on the sodium nitride nanocrystals that have grown inside the alumina pores. First, the crystallographic orientation of the crystals. As you can see here, this is an X-ray diffraction pattern of the crystals inside the pore. The area that covered by the X-ray diffractogram is about 1 square centimeter, which means we are dealing with about 100 billion crystals. You can see here only one peak, indicating that all the crystals are grown with the same crystallographic orientation inside the pore. And the crystallographic orientation can be changed by changing the parameters of the growth, for example, the concentration of the liquid solution. So here we have another crystallographic orientation than the upper one. The next stage that I would like to focus on is the piezoelectric measurements of these crystals grown inside the pores in our lab. This is the setup, and I would like to show you the results. What you see here is a modulation of the piezoelectric current as a result of a modulation of the applied pressure. Now you can see that the applied pressure, okay, decreases. As a consequence of it, the piezoelectric current decreases, and we can reach even a monitoring or detecting of pressure for 1 Pascal in an environmental pressure of 1 atmosphere, which means 5 orders of magnitude than the regular pressure where the device is formed, indicating the sensitivity of these crystals. What are the applications of these crystals as detectors? There are numerous applications that one can think of. For example, non-contact and remote ultrasound monitoring, remote infant breathing control, gas leakage detection regardless of chemistry, and sensors for intelligent systems and robots. With this, I end my presentation and thank you for your attention.